All right, so in this video, we're going to talk about dv equals rho squared sine phi d rho d phi d theta when it comes to spherical coordinates. So why is this true? And the thing that I'm most curious about is there a geometrical way that explains why this is true? Well, suppose we have a sphere. We can think of this sphere as the Earth's surface. So imagine that this point represents the North Pole, and we were to construct two lines of longitude from the North Pole down to the equator. So those are our two lines of longitude. Well, it turns out that in terms of spherical coordinates, the angle between these two lines of longitude is delta theta. Now, imagine we were to construct two lines of latitude bounded by these two lines of longitude. We'll say our first line of latitude looks something like that, and another line of latitude looks something like that. Well, the angle bounded by these two lines of latitude represents delta phi in terms of spherical coordinates. Notice how we have 4 points right here. We're going to connect each of these 4 points with the origin. Now, imagine we were to take these two lines of longitude and these two lines of latitude and project them down into the Earth's surface the same amount of distance. So what that means is, for instance, let's say we take this line of longitude and project it down into the Earth's surface like that. We're going to project this line of latitude the same amount of distance. So it's going to connect with that projection like that. And it's going to connect with the projection of this line of longitude like that. And it's going to connect with the projection of this line of latitude like that. Notice how we formed some cube-like structure right here. Well, in terms of spherical coordinates, this distance represents delta rho. Now, just to explain why these three things are what they are, well, delta rho represents the difference between these two distances from the origin. Delta theta represents the difference between these two polar angles from the x-axis. Delta phi represents the difference between these two angles measured from the positive z-axis. Right? So these three spherical constraints yield this weird-looking volume. It's sort of like a cube-like structure. So what is the volume of this cube-like structure? That's the question that we're going to answer in this video. And to take this a step further, imagine we were to shrink delta rho, so it's really small. If we shrink delta theta so it's really small, and we shrink delta phi so it's really small, that's going to cause this volume to become really small. Well then, what will this volume become? We're going to geometrically show that the volume of this thing becomes rho squared sine phi d rho d phi d theta. When delta rho becomes d rho, delta theta becomes d theta, and delta phi becomes d phi. So how do we actually figure out the volume of this thing? Well, we're going to break this problem up into a series of steps, starting with step 1. So this is our sphere. And again, we're going to think of this sphere as the Earth's surface. So imagine that this is the equator, and imagine we have some other line of latitude. Let's say that other line of latitude is right here. So the first question we want to answer is, what is the volume of the region bounded by the equator and this line of latitude? That is to say, what is the volume of this region? So what is the volume of this pink region? Well, in order to determine the volume of the pink region, we have to give this sphere some parameters. Like, for instance, what's the radius of this sphere? Well, let's say that the radius of this sphere is rho. we're also going to say that the angle forming this line of latitude, that is this angle right here, we're going to say is phi. Now, it turns out that the radius of this line of latitude forms a right angle with the z-axis. As a result, we have a right triangle right here. And that means that we can use trigonometry to determine that this side length is rho sine phi. And this side length is rho cosine phi. So, these are the four constraints for our region. So then, how do we find the volume of this pink region? Well, it turns out we can do so by integrating the volumes of a bunch of thin disks from the equator to this line of latitude. We can imagine that one of those thin disks looks something like this. We'll say that the radius of our thin disk is capital R, and the thickness of our thin disk is dz. The reason why I'm calling it dz is because we're integrating these thin disks in the z direction. So we're integrating the volumes of these thin disks. So then what's the volume of a thin disk? I'm going to call the volume of a thin disk dv disk. Well, these disks are in the shapes of cylinders. So really we're computing the volume of a cylinder, which is pi r squared h. And for our purposes, that is pi capital R squared dz. Therefore, since we're finding V1 is found by integrating dv disk, right? We're integrating the volumes of these thin disks. It's the integral of dv disk. Therefore, since dv disk is equal to pi r squared dz, we're really integrating pi r squared dz. So we're integrating with respect to z. So what are our bounds of integration for z? Well, we're integrating from the equator to this line of latitude, meaning we're integrating from a z value of 0 to a z value of rho cosine phi. So the last question we need to answer before we can evaluate this integral is, what is the radius of this thin disk? In other words, what is the radius of any thin disk between the equator and this line of latitude? Well, to answer that question, I'm going to redraw this from the perspective of just the y-axis and z-axis. So we have the y-axis and z-axis, but from the perspective of just these two axes, the sphere looks like a circle. So something like that. And the equator looks like a straight line. And this line of latitude also looks like a straight line, parallel to the equator. And the volume of our region will look something like this. So then, if we imagine a thin disk somewhere between the equator and this line of latitude, it would look something like this from the perspective of just the y and z axis. And the coordinates of this point would be the radius of the disk, comma, the z coordinate of the disk. And by the way, the equation of this circle is y squared plus z squared equals rho squared, right? Rho would represent the radius of the circle, but we know that the circle is just our way of looking at the sphere. The radius of the sphere is equal to the radius of the circle. So that's why we hit y squared plus z squared equals rho squared. So what we're going to do to determine the radius of the disk is we are going to substitute y for r and z for z. That means we get... So now solving for r, we'll first subtract z squared on both sides. And then to solve for r, we'll then take the square root of both sides. And technically, the radius of any thin disk is going to be a positive number because a radius is a length of something, and lengths are always positive. So we can choose it to be the positive square root. It turns out if it is positive or negative, it's not going to matter because we're squaring it anyway. So that's perfectly fine to call the radius this. So now we can substitute r for the square root of rho squared minus z squared. So now we're ready to evaluate this integral. notice we can pull out the pi because that's a constant. And the square of a square root eliminates the square root. So this is the integral we're evaluating. But notice this integral just involves using the reverse power rule. So we know that rho squared is a constant for this sphere. So the integral of rho squared is rho squared z, minus the integral of z squared, which is 1/3 z cubed. And so this is the result of our integral. Of course, we have our bounds of integration. So now we're ready to perform the substitutions for our bounds of integration. So first, I'm going to substitute z for rho cosine phi. And then we would subtract the substitution of z for 0. But really, if you substitute z for 0, you're going to get 0 minus 0, which is 0. So overall, you're subtracting 0. So now we can simplify this. If we simplify the inside of our overall parentheses, we will get this. And then we can distribute the pi across, we would get this. And so this would be the volume of this pink region. So we have figured it out. So now that we've found V1, we're ready to move on to step 2. So this is our sphere, and we're going to imagine that we have the same exact volume V1 as before. So imagine we have that same line of latitude, like that. So again, if you recall, volume 1 was the volume of the region bounded by the equator and this line of latitude. So what I want you to imagine is we take that region and we drill a cone out of it. So imagine we form a cone like that. Imagine we take volume 1 and we remove this cone from it. Well, the resulting volume we will call volume 2, which looks something like this. In other words, what is the volume of this region, right? So imagine we're taking volume 1 and we're removing this cone from it. That's what volume 2 is. So the way we could put it is V2 equals V1 minus the volume of this cone. So what is the volume of that cone? Well, the volume of a cone in general is 1/3 pi r squared h. So then we need to determine the radius of the cone and the height of the cone. Well, first off, let's just rewrite the constraints that we had when figuring out V1. That is, the radius of this sphere is still rho. The angle forming this line of latitude is still phi. And the radius of this line of latitude is still at a right angle with the z-axis. Therefore, by trigonometry, this radius is still rho sine phi. And also by trigonometry, this side length is still rho cosine phi. So we still have the same 4 constraints as before. Therefore, we can see from this that the radius of the cone is rho sine phi, and the height of the cone is rho cosine phi. Therefore, we can substitute r for rho sine phi and h for rho cosine phi. And then if we were to simplify this, we would get this. And also, you know what? I'm going to rewrite sine squared phi as 1 minus cosine squared phi. And so now that we have that, what I'm going to do now is I'm just going to distribute this thing across the parentheses. So this is what we get. So now we know what the volume of the cone is. Therefore, to find V2, all we're going to do is take this thing and subtract it by this thing. So I'm just going to rewrite V1 right here. Right, and we're taking that and we're subtracting it by the volume of the cone. So really, in parentheses, I'm going to rewrite this right here. So this is what we have now. So next, what I'm going to do is I'm going to distribute the minus sign across this parentheses. And that is what we get. But notice that we actually have something that cancels out. Turns out that this cancels out with this. And as for the other two terms, we can actually combine like terms. We can think of it, there's a 1 right here. I'm going to rewrite this 1/3 in red. Well, it turns out that both of these terms share pi rho cubed cosine phi. Pi rho cubed cosine phi. Therefore, we can combine like terms to get 1 minus 1/3, which is 2/3 pi rho cubed cosine phi. So this right here would be V2. And it's really interesting because it seems like we did something more complicated with volume 1, but we got something that looks way simpler, which is pretty interesting. So that's the result for volume 2. So we're ready to move on to step 3. So we're going to imagine that we have the same exact volume 2 as before. But we're going to take this volume 2 and we're going to construct 2 lines of longitude from the North Pole. Right? Just like that. We have our 2 lines of longitude. And this is where the 2 lines of longitude exist on our volume 2. We can connect these 2 points with the origin, like that, and we can connect these 2 points to the origin as well, like that. Well, as we mentioned at the beginning of this video, this angle right here we call delta theta. And so this red region is the volume that we are trying to find. So it's the volume of this red region, V3. So how do we find V3? It turns out that all volume 3 is it's going to be delta theta over 2 pi times volume 2. It's just a fraction of volume 2. And that fraction depends on delta theta. So this might make sense to some of you. Some of you might be not completely convinced. But this volume is directly analogous to finding the area of a circular sector. If you recall, the area of a circular sector looks something like this. This sector spans some angle, delta theta, and has some radius, r. Well, it turns out that the area of the sector is equal to delta theta over 2 pi times the area of the circle, which is pi r squared. And so this is directly analogous to finding the area of a circular sector. It's just, in this case, it's in 3D. And by the way, I should mention that our delta theta has to be in radians, because it's delta theta out of the full 2 pi radians in the circle. So that's why it works the way it does. So this is directly analogous to finding the area of a circular sector. So hopefully that makes sense, and we're going to use that to determine volume 3. So really, volume 2 is exactly this, so we're going to substitute volume 2 with this. Notice that the 2's cancel out and the pi's cancel out. And as a result, you're left with this as your answer for volume 3. So this would be the volume of this red region. And technically, to be complete, I should notate that rho is still the radius of the sphere, and phi is still the angle forming this line of latitude. So given these three things, this would be the volume of this red region. So that completes step 3. So now we're going to move on to step 4. Now, as for our next step, I'm not going to redraw the full sphere because it's going to get very cluttered. So we're essentially building off of volume 3. So imagine we have some volume 3. So this right here is our volume 3. And the radius of our sphere is still rho, but we're going to consider if we have two volume 3s with different angles for phi. So imagine we have this volume 3 with an angle phi A, but imagine we have another one of these volumes. Suppose this volume goes up to here, and it looks something like that. Well, the phi angle for this volume would be, let's call it phi sub b. Observe that phi sub b is greater than phi sub a. I'm going to write that right here. So we're going to say that delta phi is equal to the larger phi minus the smaller phi, so phi sub b minus phi sub a. And we're going to say that the volume 3 with phi sub a is v3a. And the volume 3 with phi sub b is v3b. So really, this is v3a, this is v3b. We're going to say that v4 is v3a minus v3b. What that means is v4 is the volume of this red region right here. So we want to find the volume of this region. So to do that, well, we know exactly what v3a and v3b are. For v3a, all we're doing is we're taking this thing and replacing phi with phi sub a. And we're subtracting v3b, which is taking exactly what this is and replacing phi with phi sub b. And so this is v4. Notice we can make this a little bit simpler to look at by factoring out 1/3 rho cubed delta theta from both of these terms. And so this is what we get. This right here would be the volume of this region. And by the way, I forgot to write that this angle would be delta theta still. So yeah, that's basically what that is. So now we're ready to move on to step 5. Again, I'm not going to redraw the whole sphere, but I'm going to redraw volume 4, which looked something like this. Right, and we're getting a little closer to what this looked like at the beginning of this video. Well, check this out. We're going to consider two volume 4s, both of which have different rho values. We could say that this volume 4 has a rho value of rho d, and let's say that we have another volume 4 that's smaller than this one. It would look something like that, and this one has a rho value rho c. Now notice rho d is bigger than rho c, and we're going to say that delta rho is equal to the larger rho minus the smaller rho, so rho d minus rho c. And again, we have the same constraints as before. This angle would be phi A, this angle would be phi B. If we project this onto the xy plane, this would be delta theta, and I believe that covers all of the constraints for this volume. So that's illustrated as best as I could do it. So with this, we're going to say that the volume 4 with rho c is v4c. And the volume 4 with rho d is v4d. And we're going to say that volume 5 is V4G minus V4C. That is exactly what volume 5 is. In other words, it's this volume minus this volume. In other words, volume 5 is exactly equivalent to this volume. And this is exactly the volume that we were looking at the beginning of this video, which is really cool. So, we're ready to compute volume 5. As for V4D, that's exactly this, except rho is rho sub d. And we're subtracting this by V4C, which is exactly this, except rho is rho c. So, this is this volume, right? That was good, because it's so much, there's so much going on, but let's clean this up a little bit. Let's factor some things out. Well, notice both of these two terms share those three things. So we can factor out these three things from both terms. So factoring that out, inside the parentheses, you would get rho d cubed minus rho c cubed. And so now that we have that, well, this looks a lot nicer. But it turns out it's actually going to be really nice if we factor this, right? This is a difference of perfect cubes. Do you remember how to factor a difference of perfect cubes? That was good, right? So turns out it's going to be nice if we factor this. And to factor something in that form, that is in the form a cubed minus b cubed, the way that you would factor this is like this. This is the factored form of this. So we're going to rewrite this using this formula. I like that word, formula. That was good. Okay. So what this becomes is rho d minus rho c times rho d squared plus rho d rho c plus rho c squared. So this right here is volume 5. So now that we've done this, it turns out we could actually rewrite this as delta rho, because that's exactly what we called it right here. So we're just going to replace this with delta rho. We can rewrite this as 1/3 delta rho delta theta times this times this. So this right here is as far as we're going to go for volume 5. And it turns out this is exactly the same volume that we were evaluating at the beginning of this video. So instead of calling this V5, I'm going to call it delta V. So this is it. This right here is delta V. So at this point, we are going to move back up to the top. And so, as promised, we are going to think about what happens if we shrink delta rho, delta phi, and delta theta. We should still note that delta rho is equal to rho d minus rho c, and delta phi is equal to phi b minus phi a. But we're considering what happens if we shrink all three of these things so that they're all really, really small. Just like that. So what happens? Well, the result of it is, for one, delta V becomes really small. But not only that, but if delta rho becomes really small, then the difference between rho c and rho d becomes really small. So rho c and rho d are approximately equal to each other. And since these radii could be anything, in general, we're just going to call it rho. Same thing for phi sub b and phi sub a. Since delta rho becomes really small, the difference between phi b and phi a becomes really small. As a result, they're approximately equal to each other. And since these angles could be anything, we'll just call it phi. So we're going to use this new information to rewrite delta v as dv. Let's see what we have. We have 1/3 d rho d theta, and then we have cosine of phi a minus cosine of phi b. Let's not worry about this right now. Let's keep this exactly the way it is. But let's pay attention to this parentheses. Since rho c and rho d are approximately equal to each other, we're saying they're both essentially equal to rho. We can write this as rho squared plus rho times rho plus rho squared, which is essentially rho squared plus rho squared plus rho squared, which is 3 rho squared. Notice that the 3's cancel out. Now I'm going to move the rho squared up to the front right here. And the real question is, what's this going to become? Well, here's how it works. We can take cosine of phi a minus cosine of phi b and divide it by phi a minus phi b. Since phi a and phi b are both really close to each other, this is approximately equal to the derivative of cosine of phi, because that's how a derivative works. So this is essentially true. Let's keep the numerator the same, but the denominator is actually negative delta phi, because essentially if you flip these two around, that becomes negated. So negative delta phi, approximately equal to the derivative of cosine phi, which is negative sine phi. Next, I'm going to multiply negative delta phi on both sides of the equation. As a result, these go away. You're left with cosine of phi a minus cosine of phi b is approximately equal to this times this. Well, the two negatives join forces to make a positive. Let's go, right? I love joining forces. And we get sine phi delta phi. Well, we said that phi b minus phi a goes to d phi. So in this case, cosine of phi a minus cosine of phi b goes to sine phi d phi. So this is what we are going to replace the parentheses with. So this becomes sine phi d phi. And as a result, if we just rearrange this, dv is equal to rho squared sine phi d rho d phi d theta. So this right here is dv. We have taken that delta v, which is this, and we've shrunken it down. It turns out it's going to be this. And so, geometrically speaking, that's how it works. So, yeah, that's pretty much the way that you could derive it geometrically. So, yeah, this is pretty much it for this video.